right, good evening, everyone. I'm Oleksii. I work on applied AI, applied research team that is responsible for the Nemotron models post-training. And today I'll be happy to share with you some details. So let's start with actually kind of definition of what post-training is. And post-training is a stage that happens after we get the base model, like solid foundation from our colleagues from pre-training team. And it is about boosting and adding capabilities as well as adding alignment. In terms of capabilities, what we are talking about, it's basically things like reasoning, long context understanding, ability to code tools and perform tasks that require multi-steps, and in general increasing models autonomy. Additionally, there is alignment, which is an important part of post-training, which ensures that the model is aligned with humans' intentions and values. Basically, things like models being safe, non-toxic, and secure. Last year, post-training has been a huge area of research, and a lot of gains and scaling actually happened at this stage. One of the illustrations is if you look at like Llama 370B model, which was released in July 2024. And if you are like in 1 year, basically post-training made a very big difference on capabilities, right? So like in July 2025, so like 1 year after, we did some post-training, including like newer techniques like reasoning, etc. And you can see for the same base model, huge gains in capabilities. And this is like a very active area of research. So this is more of a, like kind of a history slide in the sense that initially there were no post-training at all, right? So LSTMs and like pre-transformer and then transformer models up to like GPT 3.5, those actually did not have any alignment. Those were basically giant autocompletes. I mean, they still were very exciting and useful for AI researchers, but then when OpenAI released ChatGPT, they basically added alignment stage. And now not just AI researchers, now entire world is excited about those models. And that's where models became so-called assistant models, able to engage in the multi-turn conversations with users. Next major breakthrough is reasoning, which was again pioneered by OpenAI with O1 models and first kind of published in the open by DeepSeek R1 and Kimi 1.5 models. And this is where a model like Nano V2, Nemotron Nano V2 falls in. So this is basically a model that can think before answering. And again, next kind of major step function in the model's capabilities are ability to use tools and engage in multi-step solving of the task. And this is where models such as K2 Instruct and GPT-5 are, and that's where our upcoming like Nano V3 is. I can't predict the future, but like we think in the future models will be even more capable and perform even longer horizon tasks, like tasks that require potentially thousands of steps. It's not just our opinion. If you look at this plot from MITAR organization, you can see that time horizon in the sense of steps it takes to complete a task, as well as time it takes to complete the tasks for models actually growing very rapidly. All right, so let's talk, before I jump into how we post-train, let's kind of do some definitions by examples. So first one is reasoning, right? So it's kind of obvious in retrospective, but the basic idea here is model thinks before it answers, right? So like what a fabulous idea. I wish more people did that. So typically this is manifested by model having some sort of thinking trace, typically some thinking tag open, some thinking process and thinking tag closes, and the model produces a final answer. Now, while those thinking traces are entertaining to read, it's important to realize that they are a cost to a user or to an inference service provider. Basically, they are a cost you pay in inference to get a high quality answer after that. All right, so now next one is tool use and multi-step. So how multi-step is different from multi-turn? So consider this question. So I don't know if you can read, but the problem here is this: how many, like I'm asking the model, how many pounds is 100 liters of H2O2. So to solve this problem, the model decides to do 3 steps and call 2 different tools. And important points here to notice is that model decides which tool to call when by itself. It may or may not have thinking trace at different steps. It also decides itself how many steps it needs. And it also decides itself when to yield the control back to the user, right? So it kind of thought in this case that it needed just 3 steps to solve this simple problem. But you can imagine much harder problems which require hundreds or even thousands of steps. All right, so now that we kind of have those main definitions out of the way, so how do we do this post-training? And there are, like, I would say 3 main pillars. Synthetic data and supervised fine-tuning is still a very big part of it, especially for smaller models. Second one is, of course, reinforcement learning for reasoning, also called, people call it RLVR, which stands for reinforcement learning with verifiable rewards. And of course, reward modeling and RLHF, which is reinforcement learning from human feedback. It's still very important stages that you don't need, you can't skip. Okay, so synthetic data. So why synthetic data? Well, there are like several reasons for it. Obviously, it's less expensive than human data. It's more scalable, and perhaps less obviously, but maybe for researchers it's actually obvious now that this data, like from humans, it's much harder to collect high quality now, right? So we don't need data like what is the capital of France anymore, which most humans can answer, right? So we need data which looks like, you know, explain quantum entanglement to me like I'm 5 years old or something like that, right? So you need very hard prompts and very high quality responses. And today's open weight models with good licenses can do the job pretty well. Now, what are the important components for synthetic data? Like prompts that you send to the problem should be very diverse, and they should be hard enough. I don't want it to be too simple. Obviously, the teacher models that you are generating responses with are extremely important, as well as how you pick responses from potentially many candidates. One advice I would give is that you need to be very careful with it because you will get very good benchmark scores, but especially if you can train from stronger teacher. But you may hurt your capabilities outside of this synthetic data, the blend distribution. All right, so on reinforcement learning, let's start with actually reward modeling, and because this is basically a key to good post-training. And what reward modeling is we need to be able to use some sort of function or model to assign or to score potential responses from the model, right? So given a prior conversation plus like next question to the model and several responses from the model, we want to be able to assign a score to those candidates. And it can be a single score or a vector of scores like in our work, or it can also contain some explanations and now even like reasoning traces. Reward models, I would classify them in like 2 main categories. One is verifiable rewards, which is where basically here you actually don't need a model. It's some sort of formal verifier. An example that is most commonly used is mass verifier, right? So if you want to, if you are solving equations, it's very hard to solve an equation, but if I give you an equation and say x equals 2, for example, is a solution, you would be able to very easily verify if that's true or false, right? So another example is like basic instruction following, such as does model response have the right number of paragraphs, etc. So second big category is basically where you cannot do this like formal verification of an answer, right? And that's typically based on like separate AI model, which is basically often a dedicated trained reward model. This is a very active area of research. like they kind of follow the trajectory of LLM research in the sense that it used to be simple reward models with just a single score, but now we have generative reward models, now we have reasoning reward models, and now we have reward models with tools. For example, you can use like web search to kind of fact check some of the responses. All right. So, and one thing I want to mention is, I think we are one of the few labs, if not the only one, who releases our reward models. If you go to NVIDIA's Hugging Face, you will find a bunch of them, of different types. All right, so now let's look at the sort of high-level anatomy of reinforcement learning loop. Now, since we have a verifier or reward model, so how do we use RL to train a policy or agent? Or basically, like policy and agent are terms from RL literature. It's our LLMs that we are tuning. So first, we give a model a problem, right? A prompt. It's our problem. Like, let's say, example, solve this equation. And we ask it to generate several generations, so several possible solutions. We use our reward model or verifier to assign rewards to them, and then somehow we compute advantage and like policy update computation. So this is where those algorithms differ in those details, like GRPO, GSPO, reinforce, etc. Right? So they differ in the details of how you do advantage and policy update computation. But important part is they all need verifier or RM, and they all are actually inference heavy. So they need many generations, and this is where like this idea of faster AI being better AI kind of comes in play very actively, because with models that are like hybrid, right? So based on SSMs, for the larger generations, you are much more efficient than a regular transformer. Moreover, what happens is length of those generation grows, right? So if you look at the so this is an example of Nano V2 reasoning RL run on mass. So you can see mass rewards going up, but then also length is going up. Your length of generations going up, and this was also published in DeepSeek R1 paper, right? And what happens is, as model keeps getting more and more answers correct, it does so by thinking sort of harder, by spending more tokens. Again, so you are growing your batch size and you are growing the length of your generations. That's where, hybrid or in general, faster models can be better fit for like training for reasoning RL. Now, another important part is, like I said, reasoning trace is a cost, right? So it's not an entertainment, even though they are sometimes fun to read, but they are actually a cost. And you want to have higher accuracy, but you don't want to spend. You want to spend as little as possible tokens during thinking. So what we do with Nemotron V2 and above is we implement this feature called runtime reasoning budget control, which allows you during inference to kind of forcefully close the thinking tag, and the model is guaranteed to stop thinking after that. It will just produce you an answer based on incomplete reasoning trace. Now you can try it with other models, and of course we did, but if you don't train models specifically for that, what will happen is model will actually start thinking outside of the thinking trace, or maybe it will reopen a thinking trace and kind of starts to think later. So in like Nemotron, we kind of try to guarantee that that's not gonna happen. So basically, in reasoning efficiency, we think of it in terms of for the same model size, right? So we would like to see token budget on x-axis and accuracy on the y, and of course we want to move up and to the left. And here you see different lines. Different lines are different benchmarks for a single model, and you can see that there are some sweet spots you may choose depending on your application, right? So for example, if you are suddenly experiencing a peak usage, right? So you can kind of reduce the number of tokens your models are able to think, so that you can accommodate all the requests. All right, so this is a high-level overview of Nemotron Nano V2 post-training pipeline. it starts with, strong foundation from pre-training team, base model, right? And then we do massive SFT stage from synthetic data, lots of it, like 26 million examples of synthetic data from different domains and different models. On a RL stage, I would like you to notice that it's actually sequential. We have RL for instruction following, RL for function calling, RL for chat, and they are like in sequence. And then we also have like some pruning technology to reduce the model size after that. So that's Nemotron technology. I'm not going to cover it right now. Now, again, remember here the RL stages are all sequential. So how can we keep adding and scaling our RL capabilities? There are basically two ways, and I call them kind of in depth and in breadth, right? So first one is you can train, and we should, right, train longer with better algorithm and more efficient data types like MXFP8 and VFP4, and we are doing that, and the implementations of this is available in NeMo, which is open source and which is what we are using to post-train those models. And another one, what do I mean by say in breadth, right? So is we actually want to do a multi-verifier RL training where we have one single environment per capability. So this is why we also build a thing called NeMo Gym, which allows us to implement this multi-environment RL training. So for Nano v3 and like next models, we are using NeMo RL and NeMo Gym to train a model simultaneously with multiple rewards coming from multiple verifiers. For example, right, so actually let me say what environment is, right? So environment is somehow you given problems, you can either pre-generate them or like basically you have a set of problems, then you have a way to do rollouts, and that way might include tools, right? So you might want to expose certain tools to a model like Python, search, etc. And then you have one or more solution verifier. So we can have environments that are like for browser use, for software environments, etc. And NeMo Gym is able to integrate right now with NeMo RL, obviously. That's what we use, and some of the other RL frameworks like Answers and Vero support are in progress. So this is an example of Nano v3 training run. Sorry, it's kind of little font, but let me just read it, right? So I gave you like a snapshot of like 3 environments. This is like math, coding, multiple choice question answering, instruction following, workbench, structured output. In fact, there is actually more. We are training Nano v3 with more environment at the same time. But important part here is that it is a single RL run, and it's not just math going up, and then we do another RL run where coding going up, but they are all going up at the same time. And it also helps, they also sort of tend to help each other, and it also helps avoid like reward hacking on some of the easier verified environments. Yeah, so and this is basically what we are getting with Nano v3. So Brian already showed this slide, but one point to mention here is that the reason there is a bunch of capabilities on the x-axis, right, is that we try to have several environments to target specific model capabilities, and we are able to improve them all at the same time. All right, and this is my final slide. I want to emphasize that, and this is like a fact I'm most proud of, I guess, is that all of our post-training technology is open. Our synthetic data is open. You can go on Hugging Face using this link. Our human annotated data, the one we paid vendors a lot of money, is also open under CC by 4 license. Like you can use it commercially. Please do so. It's called Help Steer 3. We are working on new version too. Our reward models are open. Our RL code base and our NeMo Gym is open. And if you want to see your capability reflected in next Nemotron models, you might consider submitting us a PR with an environment that takes care of your use case. Thank you.
All right. Any questions for Oleksii?
Hi, thank you for the very insightful talk. I wanted to know, like, how do you guys make the model know the token budget? So is it like a hard token that you stop the model? Maybe the model stops mid-sentence and it's like an algorithmic approach to change it, or the model is trained to somehow understand which token it is currently generating?
So the thinking trace starts always with a sync tag and ends always with the end of sync tag. If you don't force the budget, it will just close the sync tag when it thinks it's done and answer, right? Now, during runtime, you can send it a syncing tag sort of manually using VLM or in NeMo, which is like NVIDIA inference microservice, right? So when you send it syncing tag forcefully, it just produces you an answer. Now, the second part of your question is how we did this. The recipe is actually very simple. We during the SFT during this stage, you can see that it says reasoning on off. Sorry, this is actually a typo. It's kind of from Llama Nemotron, from older models. But in the synthetic data, we actually send examples with truncated thinking traces. So model sees that sometimes it can be interrupted mid thinking, and it is forced to produce an answer. And then in a RL stage, I believe we have this like form like structured output basically, there is also a verifier that penalizes a model if it kind of tries to start thinking again.
Awesome, thank you.
Hello, thank you for sharing your model. I have a question regarding the reward function. So if you use multiple reward function during the RL training, do you give different weights to different reward model, or they are the same?
So actually, currently we do not do that. We use, like in this case, right? So when we do multiple environment training, it's basically for every prompt, like we know this is like, for example, this is a mass prompt. It goes only to the mass verifier. And this is like a coding prompt. It only goes to the coding verifier. But what you mentioned is actually an interesting area we'd like to explore because, for example, you can have two correct mass answers, right? But then you want to send them both to, say, like reward model, like general RLHF reward model, and pick the one which explains the answer better. But we are currently not doing that. That's kind of for the future.
Okay, thank you.
Thank you so much for your presentation. I really enjoyed. Like, I have I have two questions actually. Like, the first question is, like, you said just like previous presentations that the faster AI is a better AI, and the things that I don't understand is like when you, for example, if you compare deep learning model and with a biological brain, especially like when you ask a human that please answer me really quick, and like push the human to answer you quick, it's will a high chance that that person gonna just start to talk gibberish, right? Like if you give people time, they will give you a better answer. But how do you claim that, like in our deep learning models, if they are faster, they are actually better? And that's the first question. And also, like, what they are better at? Like, for example, are they better at reasoning? Are they better at memorization? Because that's one of my concerns. Because if you ask a person and that person answers you really quickly and correctly, that means that person has already seen that problem, and he was or she was fully confident about the answer. So how do you evaluate your models to make sure that your model actually didn't memorize the problem and haven't seen the problem before?
So feel like several questions here in terms of kind of working back. How do we make sure that model didn't memorize the question? Well, obviously we try to when we do training, we pay a lot of attention to data contamination, right? So that validation and testing sets didn't leak, right? So I mean nothing nothing special there. Now your person analogy, I think your person analogy kind of are more analogous to this plot, right? So this situation where you force a person to kind of answer quickly is basically saying you can only think for, I don't know, 1,000 tokens. And yes, it's true. If you force it to think for, say, 1,000 tokens and not more, you will get generally lower scores than if you allow it to think for, say, 16K tokens. But that's not what we mean when we say faster AI is smarter AI, right? So faster AI is that is more of like comparison between different persons as opposed to pushing the same person to think faster, right? Again, let's look at this plot, right? This is anatomy of not just gRPO, it's anatomy of basically most of RL loops. And what you see here is large batch size, right? And what you see here is long context. And in this scenario, basically hybrid and like SSM models are way faster, which allows you basically to do more training updates, right? So for the same compute, because we all in reality are constrained by compute budgets, etc., right? So, and in this sense, we just, for example, can do more updates and more training for the same budget.
Thank you. So in this loop, what I understand is like it's a single like a prompt, a single generation. Well, n generations just once. But then you talked about the environments, that there's tool use, there's like multi-turn stuff. So one question is, in this training, how many steps of those environments, like, is it like one tool use, like one step, or like two, or like, what is the horizon of the agent, basically, that you're using for IRL? And then if someone could, well, you said so, but if someone, for example, has a very specialized, I don't know, database or task, could further fine-tune like a long running agent on that?
So the answer to that question depends on the specific environment. I would say for some of the two-use environments we do have, we don't fix. I think we don't fix the number of steps the model can do, and it also varies, right? So the model sees examples of solving the problems with several steps, right? So there are examples that needs like 2, and like there are others that needs 5, right? So that depends on problem and environment as well as so that depends on basically problem. So this is why, like in this situation, it's not like the model was trained to do it in 3 steps. It just decided that for this specific problem, after it got results of step 1 and step 2, it just kind of decided that it's done by itself. So it wasn't told that you can only do 3 steps.
Okay. Yeah. Thank you.
Two quick questions. First, many researchers start to align the models to express some uncertainty during the generation. Like, for example, this question, I know the answer confidently, and some say, I don't know this answer. Maybe they even refuse to answer the question. Have you tried to do something with Nemotron?
Well, we have to do this, especially for the models that are tool capable, right? So, like, if you ask it, find me best Black Friday deals on, I don't know, Sony headphones. If you don't expose search tool to it, it should refuse. It should say, I actually don't have access to a search tool right now. So yeah, we do that.
Okay, great. And the second question, have you tried something like reinforcement learning from internal feedback, when you reinforce trajectories that lead to more confident answers in the end?
So short answer is no, but there is a related point I want to make is we also monitor entropy during RL training, and what we notice is that sometimes entropy goes like way down, and it's like reward goes up, entropy goes down, and it's not necessarily a good thing because model becomes very confident, responses very non-diverse. So there is a need to keep entropy not kind of very low, but also not very high. So that's kind of, I would say, it's a research area right now. So I actually don't have a good answer. But I think it's related to model being confident or not in its answers.
Thank you very much, and thank you very much for the great talk.
Yes, thanks, Oleksii.
Thanks.